This is the 10th video in a series devoted to abstract algebra. In the previous video, we looked at the notion of a coset, and we proved some things about cosets in general, as well as we looked at lots of examples of cosets. And now we want to prove one of the most important results involving cosets. That's called Lagrange's theorem. But before we get to that, let's maybe recall some definitions. So given a group G, a subgroup H of G, and an element little g of G, then the left coset of H with representative G is written like this. So we have GH, and it's going to be all G multiples from the left of elements of H. So we've got G times H as H runs through all of H. So this is a left coset, but we defined a right coset also in the last video, and I'll let you check up on that if you want to. Essentially, anything you can prove about left cosets, you can also prove about right cosets. So we'll just stick with left cosets. And then last time, we proved that the left cosets or the right cosets partition a group into equal-sized parts. So we showed that they did not overlap unless they were the same coset, and then they also union to the whole group. And then furthermore, each coset kind of obviously has the same number of elements as H itself, given this formula right here. And then we also defined something called the index of a subgroup, and it had the following notation. So we would read this as the index of H in G is the number of left or the number of right cosets of H in G. We also proved that those two numbers were the same. The number of left cosets is equal to the number of right cosets, which is obviously important because otherwise this would not be a well-defined quantity. So now we're going to prove Lagrange's theorem, which, like I said before, is super important. And then we're going to look at lots of nice applications and corollaries of this theorem. So let's see what it says. If G is a finite group and then H is a subgroup of G, then the order of G is equal to the index of H in G times the order of H. So we've got this nice like multiplication problem between the size of H, the size of G, and the number of cosets of H in G. And now, in particular, this means that the order of a subgroup divides the order of a group. So let's say you've got a group of order 15. Well, then you cannot have a subgroup of order 10 because 10 does not divide 15. But you could have a subgroup of order 3 or a subgroup of order 5. Now, whether or not you actually get a subgroup of order 3 and order 5, well, that's yet to be determined. The converse is not true, and we'll see an example today of how the converse is not true. Okay, so let's get to the proof here. So let's maybe set M equal to this index. So the index of H in G, which means there are M distinct left cosets. And let's make a list. So, and we'll take G1, G2, all the way up to Gm, which are elements of G, so that the cosets G1H, G2H, all the way up to GMH are all distinct. So what that means is that they are disjoint, and not only are they disjoint, but they union to the whole group. But then also, let's recall the following fact, and that is the order of GIH is equal to the order of H, and this is true for all I between 1 and M. So in other words, these cosets are the same size. And you know, we never really wrote down a proof of that, but you can do a fairly simple set theoretic proof as follows. You can define a function, I'll call that function fi, and it'll go from H to the coset GIH. And what it'll do is it'll take an element little h as an input, and it'll give us the GI multiple of little h. So it'll give us GIH. And then I'll let you guys check that this is indeed bijective. So I'll maybe put that check as a bit of a homework exercise. There's not really much to checking that that's bijective. It's not a homomorphism or anything. It's really just a set theoretic map. But since it's bijective, that means these two sets have the same size. Okay, but now we're essentially ready to finish this thing off. So let's take the order of G. But notice the order of G will be equal to the sum as I goes from 1 up to m of the order of GIH. That's because the union of these cosets is the whole group, and these cosets do not overlap. So we haven't double counted or triple counted any of the elements here. But now let's notice that all of these have the size of the group as their size. So we have the sum as I goes from 1 to m of simply the size of H. But what if we add H to itself m times, or really I should be saying the order of H to itself m times? Well, then I get m times the order of H. But now replacing m with our shortening notation up here, we'll see that this is equal to the index of H in G times the order of H. But that's exactly where we wanted to end up. So now, before we move on, I'm going to do a very quick corollary down here, and then we'll look at some examples. Corollary will say the following. So if G is a finite group, I'll just write that as the order of G is less than infinity, and little g is in G, then the order of little g as an element, we'll write that as ord G, divides the order of the group. But then that follows us to see that G to the power of the order of the group is the identity. So if we can prove that first thing, then this other one follows pretty quickly. Okay, so let's see how this proof might go. Well, it's a corollary of Lagrange's theorem, so perhaps we should use Lagrange's theorem, and that's exactly what we will do. So let's take H in this case to be the cyclic subgroup generated by G. And then let's notice that the order of H is equal to the order of little g, just by that duality between a cyclic subgroup and the element. But we know from Lagrange's theorem that the order of H divides the order of G. But if the order of H is the order of little g as an element, then that means immediately that the order of little g divides the order of the group. To follow this up to this right here, that means that the order of the group is equal to the order of the element times some number, which I'll maybe call k. But then if you raise little g to this power, then you'll have little g to the order of little g all raised to the k power. But that's just the identity to the k power, which is the identity. So that gives us this like sort of bonus result here. Okay, so now let's look at some examples. So let's look at this nice, really arithmetic example based off of what we saw with Lagrange's theorem. So let's say we've got a group, and that group has 48 elements. And then we've got this string of subgroups. So H is a subgroup of G, and then K is a subgroup of H. That makes K also a subgroup of G. And then let's suppose that the order of K is equal to 8. Then we'd like to determine the possible values of the order of H. Okay, so let's get to it. So what do we know from Lagrange's theorem? Well, we know that the order of H must divide the order of the group because H is a subgroup of G. But the order of the group is 48. So let's put that here. That's because H is a subgroup of G, and we applied Lagrange's theorem. But we know something else as well. We know that the order of K, which is 8, must indeed divide the order of H. And that's because K is a subgroup of H, and the order of K is 8. So what do we have here? We have H is a divisor of 48, and the order of H is a multiple of 8. And now let's work through this as follows. Let's take 8, which is the order of K, so let's write that here. The order of K is equal to 8, and then we'll put 48 down here, which is the order of the whole group. And now let's look if we can find divisibility strings between 8 and 48. Well, let's keep this in mind. So we'll keep in mind the fact that 48 divided by 8 is equal to, let's see, I think it's equal to 6. Okay, so that means we can get between 8 and 48 two different ways. We can multiply by 2 first to give us 16, and then we can multiply by 3 to get us 48. Or we could multiply by 3 first to get us 24, and then we could multiply by 2 to get us 48. And those are the two possible paths from 8 to 48 in, what is essentially like a partially ordered set of divisors of 48, for what it's worth. I use some fancy words there. It doesn't really matter so much, but those are the two possible paths. Okay, so what do we really have here? Well, H is between K and G. That means the order of H has to be somewhere in this picture. So it could be equal to K. We could have a non-proper subgroup, which means the order of H is 8. It could be equal to G. So that means it's a non-proper subgroup of G, which means the order is 48. Or it could be in the middle with these other two numbers. But any way you stack it, you have the order of H comes from the following set: 8, 16, 24, and 48. Okay, so now let's move on to a nice example showing that the converse may not be true. This next example is super important because it'll prove that the converse of Lagrange's theorem is not true. Let's recall the moreover part of Lagrange's theorem that says that the order of a subgroup always divides the order of a finite group. And so the converse would be something like, well, if we've got a finite group and we've got a divisor of the order of that finite group, then we can find a subgroup of that order. And that's what we'll show is not true. And we'll do that with something called the alternating group on 4 letters, A4. And we haven't introduced AN in general, but we will in a forthcoming video. So I'll just take A4 to be the following subset of S4, which you can check is closed under everything you need it to be closed under for calculating subgroups. So it's got these elements. It's got 1, and then it's got all possible 3 cycles. So like 1, 2, 3, 1, 3, 2, 1, 2, 4, 1, 4, 2, so on and so forth. So those are all the possible 3 cycles. It's also got these 2 plus 2 objects. And when I say 2 plus 2, they're a product of 2 disjoint 2 cycles. So we've got 1, 2, 3, 4, 1, 3, 2, 4, and 1, 4, 2, 3. And those are all of the possible products of disjoint 2 cycles. So like I said, this is called A4. It's a subgroup of S4. Now let's notice that the order of A4 is 12. But we will show that there is no subgroup of A4 with order 6. Okay, so let's do that. So we'll do this by way of contradiction. And this is like such an important result that it's one of those to like keep in the back of your mind at all times. In fact, if you're taking a course like this, it's not out of the realm of possibility that you might be asked to recall this sort of example or counterexample for the converse on an exam or something. Okay, so anyway, back to the proof. By way of contradiction, let's suppose that we have a subgroup of A4 such that the order of that subgroup is equal to 6. And then we'll come up with a problem there. Okay, so now let's notice that if we've got a subgroup of order 6, then the order of the subgroup H inside of A4 is equal to 2. And that's just by Lagrange's theorem, just writing that kind of multiplication problem around. We have the index is equal to the order of the group over the order of the subgroup. So next up, let's notice that H has 6 elements. But if we look at all of the elements of A4, we'll notice that there are 1, 2, 3, 4 that are not 3 cycles. But if there are only 4 that are not 3 cycles, that means that H must contain a 3 cycle. And furthermore, A4 has 8 3 cycles, so that means there must be a 3 cycle outside of H as well. So let's maybe make that observation here. So observe that there must be 3 cycles in H and outside of H. So that's by just that counting argument there. There are 8 3 cycles. Well, H only has 6 elements, so it can't have all of the 3 cycles. And then there are 4 non-3 cycles. So in order to get 6 elements in H, we've got to have at least 2 3 cycles in fact. Okay, so now we're gonna take a 3 cycle that's inside of H, and we can actually, without loss of generality, assume that it has a certain form. And that form will be 1, 2, 3. So we'll assume that 1, 2, 3, that 3 cycle is inside of H. And if that seems problematic to you to assume that that distinct 3 cycle is in H, well, essentially what you can do is take the 3 cycle that's in H and just rename the numbers 1, 2, and 3 until this one is inside of H. Recall that this is thought of as the set of permutations on the set 1, 2, 3, 4, but it's really on any 4 letters, and you can rename those letters as needed. Okay, so we've got 1, 2, 3 in H, and then let's also take an element G, which is outside of H. So it's in A4, but it's not in H. But now let's recall that cosets partition a group, and there are exactly 2 cosets. And one of those cosets is equal to the subgroup itself, H, and another one of those cosets is GH. So those are the only 2 cosets. But like I said, they partition a group. That means their disjoint union is the entire group A4. So we have something like that. But then also, left cosets don't only partition a group, right cosets also partition a group. So that means that we also have A4 can be written as the disjoint union of H with the subgroup HG. Okay, so left and right cosets partition a group. Okay, but now let's compare some things. Notice we've got this decomposition, H disjoint union HG must be equal to this disjoint union, H disjoint union GH. I think it's pretty clear that since those are both disjoint unions, they both contain H, that means the other parts also have to be equal. So here's what we have. We have GH is equal to HG. But now let's put that in terms of elements. What does that really mean in terms of elements? It means for all little h in H, there exists something that I'll call an H prime, such that GH is equal to H prime times G. So why is that? Well, notice that we've got G little h is in here, which means it's in here, but the fact that it's in here means we can write it as H prime G. But now let's rewrite that a little bit and get the following nice formula. We have GH, G inverse is equal to H prime, but H prime is inside of H. Okay, but now let's remove some of the extra stuff here and see exactly what we have. So for all little h in H and little g actually inside of G, it doesn't even matter that it's outside of H in this case. We have GH, G inverse is inside of H. So maybe we could talk this through. Like if little g is in H, this is like totally trivial because we're combining things from H. But if little g is outside of H, because of this calculation right here, we get that. So if you've seen this stuff before, you know that subgroups that have this property have a special name, which we'll look at in a previous video. So now we'd like to apply this setup And just to be clear so that we know what I mean by this setup, I mean this rule right here, which I'm boxing in orange. And then we'll write that here. So apply this to the element 1, 2, 3. Yeah, the element 1, 2, 3, which, like we said before, we decided was inside of H by this right here. Okay, so now what we're gonna do is just take some semi-randomly chosen elements of our group. Oh, let's recall our group was really A4, so we could replace that with A4 and do this calculation and see what happens. So for this first one, let's set G equal to the cycle 1, 2, 4. So we don't know if that's inside of H or outside of H. But what we do know is if we do this conjugation action, that's what this is called, maybe more properly conjugating, we'll end up with something in H. So we have 1, 2, 4, 1, 2, 3, and then 1, 2, 4 inverse, which is 1, 4, 2. So that's exactly this action right here with this choice of G and then this H in H. So let's call this H. But now if we do that calculation, I'll let you do it like super carefully, but what you'll get is 2, 4, 3. But we're guaranteed that 2, 4, 3 is in H by this orange box. So we know that this is in H. Okay, but then also H is closed under taking inverses because it's a subgroup. So immediately that implies that 2, 3, 4 is also in H. So now let's maybe look at the elements that we know are in H so far. So let's write it like this: known elements of our subgroup H. So let's see, what do we know is in there? So we know the identity's in there because it's a subgroup. We know that 1, 2, 3 is in there, so 1, 2, 3. But then let's recall that it's closed under inverses, so that means 1, 3, 2 is also in there. So we've got 1, 3, 2 is also in there. Oh, but we just determined that 2, 4, 3 is in there. So we know that 2, 4, 3 is in there. And then by inverses, we know that 2, 3, 4 is also in there. So that gives us 1, 2, 3, 4, 5 elements. But that means we've only got room for one more element. But let's recall that our group is closed under multiplication, or under composition in this case. So let's combine 1, 2, 3 and 1. So let's combine 1, 2, 3 with 2, 4, 3. So let's do this off to the side. So 1, 2, 3 and 2, 4, 3 is equal to, well, I'll let you work out all of the details, but that's equal to 1, 2, 4. Okay, but since, like I said, 1, 2, 3 and 2, 4, 3 are in H, that means 1, 2, 4 is in H. So let's put that here, 1, 2, 4. Oh, but 1, 2, 4 is in H, so that means its inverse is in H. But its inverse is 1, 4, 2. Oh, but I think something strange or wrong is afoot here. Let's count up the number of elements we have in H. We have this one right here, the identity, that's 1. We have this one right here, 2. This one right here, this one right here, 3, 4. This one right here, 5. This one right here, 6. This one right here, 7. So we found 7 elements of H, but H was only supposed to have 6 elements. So that brings us to our contradiction. But like really looking back on it, what did we contradict? Well, we contradicted this original assumption of possibility that we could find a subgroup of A4 with 6 elements. So since we've contradicted that possibility, that means in fact there is no subgroup of A4 with 6 elements. And that essentially establishes the falseness of the converse of Lagrange's theorem. Okay, so all of this said, there are some partial converses of Lagrange's theorem, and we'll see some of those as we move forward with material. Okay, so now let's move on to some more corollaries. So the next corollary starts doing the thing of classifying different types of groups. And it says, essentially in words, that all groups of prime order are cyclic groups. But we could also write it like this. So if P is prime and the order of G is P, then G is isomorphic to ZP. So let's see how this goes. This is actually going to be quite quick. So let's take an element which is not the identity inside of G, and let's notice that the cyclic subgroup of G is, well, it's a subgroup of G. But then also, since E is not equal to the identity, we know that the order of this cyclic subgroup is not equal to 1, but since it's a subgroup of the whole group, we know that the order of this cyclic subgroup divides the order of the whole group, which is P. But we've got a number that divides a prime, but is not equal to 1. But primes only have two divisors, 1 in themselves. So that means that this number, which is the order of this cyclic subgroup, is equal to the prime. Well, what does that mean? That means we've got a subgroup which has the same size as the whole group, and everything is finite. So in the end, that tells us that our whole group is actually just equal to this cyclic subgroup. But let's also recall that cyclic groups of finite order are all isomorphic to ZP. Whereas if you also recall, cyclic groups of infinite order are isomorphic to, let's see, it was just the integers. Okay, so let's do another quick corollary. Here's our next corollary to Lagrange's theorem, which in its own right is a very important number theory result. But generally, if you just take a number theory class, you don't get it via group theoretic methods. So this is like kind of a different proof than you would see in a class like that. Okay, so anyway, let's get to it. For all integers a and natural numbers n, where the GCD of a with n is 1, we have a to the phi of n is congruent to 1 mod n. I think we recalled what phi of n was in a previous video. That's Euler's totient function. Maybe look that up or remind yourself of that if you need to. So this thing is called Euler's generalization of Fermat's theorem, or sometimes just Euler's theorem. But thinking of it as Euler's generalization to Fermat's theorem, you might say, well, what's Fermat's theorem? Well, it's exactly this case right here if you have a prime, and I've written that here. So if n is equal to p, a prime, then a to the p minus 1 is congruent to 1 mod p. That's because phi of p is equal to p minus 1. Okay, so let's look at the proof here, which is also quite short. So let's maybe note that under this setup, where we have a relatively prime to n, we have the equivalence class of a can be thought of as an element of un, the group of units modulo n. And then let's also recall that the order of the group of units modulo n is equal to phi to the n. But that's essentially going to take us all the way home, because by our first corollary, we know that the order of an element of a group, so the order of A, it divides the order of the group, but the order of the group is phi of n. But what does that tell us? That tells us that this equivalence class to the phi of n power is equal to 1, and let's recall that this is all occurring within the group of units un. But then we could maybe simplify this a little bit to rewrite this as the equivalence class of a to the phi of n is equal to, I should really have an equivalence class of 1 here inside of u of n. But what does it mean for those equivalence classes to be the same? Well, that's exactly the same as saying that a of phi of n is congruent to 1 modulo n. And there's our result. Okay, so now let's look at a nice quick application of this sort of result that will tell us something about the types of primes that allow us to have the square root of minus 1. Now we're going to look at a nice application of Fermat's theorem. So this tells you what primes allow you to have the square root of minus 1, essentially. Let's see what it really says. So if p is a prime of the form 4n plus 3, so it's a prime that's congruent to 3 mod 4, then there is no solution to the congruence x squared congruent to minus 1 mod p. Okay, so let's get to this. So we're going to do this by way of contradiction. So by way of contradiction, let's suppose that we have an integer x such that indeed x squared is congruent to 1 modulo p. Okay, nice. But now let's notice that x is not divisible by p for sure. And that's because if x were divisible by p, then it would be congruent to 0 mod p, which means its square would as well, which means it wouldn't satisfy this equation. So, but not being divisible by p means that we can use Fermat's little theorem. So let's do that. But we'll do that by raising this whole action, or our number x, to the p minus 1. So let's write that out. So let's note that we have x to the 4n plus 2 is the same thing as x to the p minus 1, but that's got to be congruent to 1 modulo p, and this is by Fermat's little theorem, like I said before. But now let's also notice that if we look at x to the 4n plus 2, that's going to be the same thing as x to the power 2, all raised to the 2n, times x to the power 2. Okay, well that's just by moving exponents around, right? But this is going to be congruent to minus 1 to the 2n times minus 1 modulo p. That's because x squared is congruent to minus 1 mod p. Oh, but look at this. Minus 1 to the 2n is just 1. So in the end, we get this whole thing is congruent to minus 1 mod p. And now the issue is already on the chalkboard. Let's notice that simultaneously we have x to the 4n plus 2 is congruent to 1 mod p, and x to the 4n plus 2 is congruent to minus 1 mod p. But congruence mod p is transitive, so that means 1 is in fact congruent to minus 1 mod p. Just using, like I said, the transitivity through x to the 4n plus 2. Now let's look carefully at the definition of congruence mod p, and let's note that this tells us that p divides 1 minus negative 1, which is 2. So we've got p, our prime, must divide 2, but there's only a single prime that divides 2, and that is the number 2. So p equals 2. Oh, but that's our problem because we assumed our prime was of the form 4n plus 3. But if p is of the form 4n plus 3, we know that p is bigger than or equal to 3, because n here is taken to be 0 or larger. We've simultaneously got p is equal to 2 and it's bigger than or equal to 3, so that gives us our contradiction, contradicting our assumption up here that it was possible to solve this congruence. Okay, so now let's prove a really important result regarding the types of groups of order 2 times p. Now for a nice big classification type result. I really like this result. So let's suppose that p is an odd prime. Well, in the case when it's an even prime, the equal to the number 2, the same kind of thing holds, but it holds maybe without all of the work. So you could actually maybe do that as a homework exercise. Okay, anyway, back to it. Let p be an odd prime and g be a group of order 2 times p. Then g is either isomorphic to z2p or g is isomorphic to dp. So it's either that cyclic group or it's a dihedral group. Okay, so let's see how this proof goes. So maybe the first little case that we might want to deal with is what happens if g has an element of order 2p. So let's write that here. So we have g inside of g such that the order of little g is equal to 2p. Let's notice that that means immediately that the group is equal to the cyclic subgroup generated by that element, because that cyclic subgroup will also have order 2p. It'll fill out the whole group. But that cyclic subgroup is isomorphic to Z2P by the fact that cyclic groups are always isomorphic to Zn or Z. Okay, so that's our first case done. And now let's move on to our second case, which is G doesn't contain elements of order 2p. And now we're going to make a little bit of a subclaim here. This subclaim is really important, and it's like fairly similar to some stuff that you see a little bit later in a course like this. Okay, so this subclaim says that G has an element of order. Okay, well, let's maybe see how the proof of this subclaim goes. Let's do this by way of contradiction. So by way of contradiction, suppose not. So in other words, we're supposing that G does not have an element of order P. But let's recall that the order of an element has to divide the order of a group. But that means that the only possible order of an element left is 2, because the only divisors of 2p are 2 and p, or 1, I guess. But there's only a single element of order 1, that's the identity. So all of this puts together to the following statement. So all non-identity elements are order 2. Okay, so now that's good. Now let's take A and B to be distinct elements inside of G. And they're also distinct and they're non-identity. Okay, good. And now let's consider the following set. We'll consider the set which contains the identity. It contains A and B, and then it also contains A times B. And let's notice that this is in fact a subgroup of G. This closes under multiplication. I think it pretty clearly closes under multiplication. A times B is AB. A squared is the identity, B squared is the identity. Well, AB squared is also the identity. And it's also the identity because everything that's not the identity squares to the identity. Furthermore, AB times B is A, and then so on and so forth. So you can maybe do all the calculations on your own. You also get that the fact that this is an abelian group, but I'll sort of leave that to you. Okay, but now let's note that this means that the number 4 divides 2 times p. That's because the order of a subgroup always divides the order of a group. This is order 4, that must divide the order of the whole group 2p. Oh, but that means that the number 2 divides p. But if 2 divides p, that means that p is even, but that's a contradiction because up here we assumed that p was an odd prime. Okay, so that means that we indeed have an element of order p. Now let's take that element. So let's take h inside of G such that the order of h is equal to p. So that's possible by the proof of this claim. And now let's form the following subgroup. I'll call it capital H, but it'll simply be the cyclic subgroup generated by H. And like I said, let's notice that that is a subgroup of G. Furthermore, the index of G in H is equal to the order of G divided by the order of H. The order of G is 2p. The order of H by construction is p, so that means this index is 2. Now we're going to play the same game that we did before with our A4 example. So let's take an element G outside of this cyclic subgroup H, and notice that that gives us 2 distinct cosets, H and GH. And because of this index action, their disjoint union is the group itself. Okay, so we're kind of running out of room. Let's take this information up and then we'll keep going. Okay, so quickly, where are we? We have H's and G, it has order P. That means we can form the cyclic subgroup out of little h, which we'll call capital H, which is a order P subgroup of G. And then we'll take a G outside of this subgroup. There are plenty of G's to pick from. And then we'll form the coset decomposition, G as a disjoint union of H and the left coset in H of G. Okay, and now let's consider the following additional coset. So we'll consider the coset G squared H. And let's notice this is a coset, but we know there are only two cosets by that index. So that means there are really two possibilities. We have G squared H could be the identity coset, which is the subgroup itself, or G squared H could be equal to the coset GH. And we're going to go through these one at a time to see which one is impossible, and thus the other one must be true. Okay, so let's go through this first case, which is G squared H is equal to just the original subgroup. But let's recall by that big theorem that we had in the previous video about coset equality, this implies that G squared is an element of H. But then that tells us that the order of G squared must divide the order of H, which is P. Okay, but that means that the order of G squared can either be 1 or the order of G squared has to be equal to P. But now if the order of G squared is 1, that means that G squared is equal to the identity and we're done. But if the order of G squared is P, then that actually brings us to an issue. That means G to the 2P is equal to the identity, which means that the order of G is equal to P. Well, we know that G squared is not the identity because its order is P, but we also know that G doesn't have any elements of order 2P. That was one of the original assumptions. But then if the order of G is equal to P, then that means that G generates the same cyclic subgroup as G squared. And furthermore, G squared is inside of H, which means that this is a subgroup of H. But if that's a subgroup of H, then that means that G was inside of H. But that's our contradiction because we assumed that G was not in H. Okay, so what does that mean? That means that all of this stuff over here is impossible. So this cannot occur, which means we in fact have the order of G squared is equal to 1, or the order of G is equal to 2. So let's finish that off here. The order of G is equal to 2. Great. You might say, well, how do we know it's not equal to 1? Well, notice G is outside of the subgroup, and there's only one element of order 1, and that's the identity, but the identity is inside the subgroup. So the order of G can't be 1, it has to be 2 here. Okay, so now let's look at our second case built off of these coset possibilities. So let's put that right here. So case number 2 would be that the coset G squared H equals the coset GH. But now let's apply our theorem about coset equality again, and that means that G squared times G inverse is an element of H. So recall that we had XH is equal to YH if and only if XY inverse was in H, or something like that. But now notice this simplifies to G is inside of H, which is a contradiction again, because we assumed that G was not in H. Okay, so let's see what we had. We took a G outside of H, but this was chosen arbitrarily. So that means we took any G outside of H, and we showed that its order had to be 2. So let's maybe put that up here, and then we'll erase some things and then keep going. So up here we can put that the order of G must be equal to 2. And so this is an important structural thing that we have here. We've got an order of element P inside of G. That forms a cyclic subgroup. If you take anything outside of that cyclic subgroup, it has order 2. Okay, so now let's keep going. Okay, so now let's take our element h, which was order p, and our element g, which was order 2, and look at hg. But that hg is in the coset hg. But kind of in parallel to what we did before with the breaking g up with cosets, we can do the same thing with a right coset. So we have g is equal to h disjoint union hg. But notice if hg is in hg, then that means it's not inside of h. So let's write that down. So hg is outside of h. But on the previous board, we proved that everything outside of h was order 2. So that means we know the order of hg is equal to 2. Okay, but that means we know the identity is the same thing as hg squared, which is the same thing as hg. Okay, but now let's right multiply by g inverse and then h inverse to see where that takes us. So let's maybe put it like this. We're right multiplying by g inverse, h inverse. So that's going to give us g inverse, h inverse is equal to hg. So something like that. But luckily we know g inverse and h inverse given the orders. So g inverse is equal to itself because g has order 2. H inverse is h to the p minus 1 because h has order p. So let's see, we have hg is equal to gh to the p minus 1. And then by induction, which we essentially did before, starting with something like that, we have hg to the k is equal to g h to the p minus k. And now everything should be starting to look pretty clear. Now we can list the elements of g as follows. We have e, and then next we'll have h squared, h cubed, ending at h to the p minus 1. So those are all of the elements of h. And then we can write all of the elements outside of h. And that'll be g, gh squared, all the way up to gh to the p minus 1. Notice that's everything in the coset gh, because h was that cyclic subgroup. Okay, but now we can write dp under here, and notice that we've got like a very obvious map. Here's the identity, here's r squared, here's r cubed, all the way up here to r to the p minus 1, and then we'll have sr squared, all the way up to sr to the p minus 1. And now if we define a map that does this, just like right down the columns, that's like quote unquote easy to check that this is an isomorphism. But really all you need is that g is in fact generated by little g and h, where g squared is the same thing as h to the p is the identity. And furthermore, we have hg is equal to gh to the p minus 1, which we derived all of those identities already. But that's exactly sort of the generators and relation rule for making dp in the first place. So when all is said and done, we have that our g is in fact isomorphic to dp. Putting that together with the first case, we see that G is either that cyclic group or that dihedral group. Okay, nice. Now let's look at a quick application before I leave you with some warm-ups. Here's a quick application of that result. And this is groups of order 6. So 6 is 2 times 3. 3 is obviously the smallest odd prime. So our result proved that G is isomorphic to Z6 or D3. Now, in the abelian case, you can easily think of 2 possible groups of order 6, Z6 or Z2 cross Z3. But since those are both abelian groups of order 6, they must be isomorphic. Notice, in fact, this is all of the isomorphic ones, and this is all. So in fact, this represents all of the abelian ones, whereas this represents all of the non-abelian ones. Okay. So in the non-abelian case, we have isomorphisms between the following 3 groups: S3, D3, and then this new one, GL2, Z2. Let's briefly explain what that is. So that's going to be all 2 by 2 matrices where the entries are in Z2 and the determinant is non-zero. So in other words, they're invertible matrices. But if you look at all of the possibilities, there are only 6 elements here. Notice there are only 16 total matrices in the first place. That's because you've only got 2 choices for all of the entries. But if you require them to be invertible, you only get 6. And there's the identity matrix, 1, 1, 0, 1, 1, 0, 1, 1, and then this bottom row as well. And then you can check that this is non-abelian by perhaps multiplying some choice of these in either order. Maybe you could do this times this versus the opposite order and see that you don't get the same result. I'll let you check that it's non-abelian. But since it's not abelian in order 6, it has to be isomorphic to D3 or S3. Well, those are the same. Okay, so now I'm going to leave you with some warm-ups. Here's some warm-up exercises. So let's start with a group of order 60 and determine the possibilities for the orders of the elements of G. Next, suppose we've got a string of subgroups. K is a subgroup of H, which is a subgroup of G. And then the order of G is 360, whereas the order of K is 15. What are the possible orders of H? Then finally, let's take G to be a group of order 9 and show that G could only be Z9 or Z3 cross Z3. And that's a good place to stop.